Welcome everyone. In last video, we understand the working of the asynchronous counters. From this video, we are going to start understanding the working of the synchronous counters, and we will consider our example of an up counter. There are few steps to design a synchronous counter. From book to book, number of steps may vary. The description of the step may vary. There is no hard and fast rule that you need to follow these steps only. You can change the number of steps according to your understanding. But beginning, you need to follow some of the steps. The first step is that how many number of flip-flop we require to design a counter. That we will see that how we can find this number of flip-flop. Step 2 is we need to make a state diagram of the counter. Those who know what is a state diagram, that is well and good. Otherwise, we will see in the upcoming slides. The third step is we need to select that what is the type of the flip-flop we can use. Till now we have studied many different types of flip-flop. We can design the synchronous counter by using any type of flip-flop. So in the third step we are going to choose what type of flip-flop we can. The fourth step is we need to make the excitation table of the flip-flop. If you know the truth table of any of the flip-flop, converting the truth table into the excitation table is very easy. We will see in the upcoming slide how we can convert it. Step 5, we need to make a state table of the counter. State table is just the combination that what is the present state and what would be the next state for this counter. Step 6 is we need to map this excitation table over the state table. This is just the mapping of excitation table over the state table. In the last and in the final step, we are just going to find the equations or Boolean equations which we can use to make the circuit diagram of the final counter. Now let us move to the first step for designing a synchronous counter. Let's consider an example that we are going to design a 2-bit synchronous up counter. The first step is that we need to find the number of flip counter you need to design. The number of bit you need to design that is same equal to the number of flip-flop you require. So for this example, we require 2 flip-flop. If let's suppose I need to design a 3-bit counter, then I require 3 flip-flop, and if I need to design a 4-bit counter, I require 4 flip-flop. So in this first step, what my answer is that I require 2 flip-flop. In second step, we need to make the state diagram of the counter. I know my counter is 2-bit up counter. For 2-bit, what are the possible state we have? One is my flip-flop B at 0, A at 0. Or I can say that my counter is at the state of 0, 0, which is equivalent to 0. My counter may be at the state of 0, 1, which is equivalent to 1. It may be at the state of 1, 0, which is equivalent to 2, and at the last 1, 1, which is equivalent to 3. So possible state which I have is simply 2 raised to power n, where n is the number of flip-flop you require, or n is the number of bit you require. A counter can count in the upward direction. It means what is up counter? After 0 it will display 1, after 1 it will display 2, after 2 it will display 3. So how we can make a state diagram? This is 0, 0 state. After 0 it go to 0, 1. After 0, 1 in the next clock it go to 1, 0. In the next clock it go to 1, 1. And in the fourth clock it come back to 0. 0 initial state. So you can see In this, it will be count in kind of clockwise direction, you can say. Down counter, which will count in the decreasing order. That after 3 it will show 2, after 2 it will show 1, after 1 it will show 0, and after 0 it will again display 3. On this side we have the state diagram for down counter. After 0, after first clock it will show 3, after 3 it will show 2, after 2 it will show 1, and in the fourth clock it will again come back to 0, 0. This is for 2-bit counter. In third step, we need to identify the type of the flip-flop which we are going to use. I can use SR flip-flop, I can use D flip-flop, JK and T. Any flip-flop we can use, there is no issue. But most of the time in designing process for the synchronous counter, we are preferring the T flip-flop. It is easy. In the designing part, you will see why it is easy. The next step is we need to make the excitation table of the flip-flop. We have selected the T flip-flop, so we are going to make the excitation table of the T flip-flop. But for excitation table, we require the truth table of T flip-flop. The truth table of T flip-flop is the input T I have and two output I have, Q and the Q bar, output and its complement. If the value of the T is 0, it is the no change condition of the T flip-flop. It means the value of Q remain Q and value of the Q bar remain Q bar. There is no change. But if the T value become 1, then it is the toggle state of the T flip-flop. It means the value of Q bar become Q and value of Q become Q bar. This is toggle state. From this truth table, we can make the characteristic table of the flip-flop. In characteristic table, we are going to consider two input of the flip-flop and the previous output of the flip-flop, which is already stored on the flip-flop, and Q plus indicating the next state. Possible combinations are if T is 0, Q is 0, Q value stored is 0, and if T is 0, according to the truth table, it is no change. If previous value is Q, which is 0, the next value Q plus is also 0. If the previous value is 1, the next value is also 1. But if the value of T is 1 high, toggle state, then the value 0 which is stored on the Q become 1 when the clock comes, and value of 1 become 0. So this is the expand version of the truth table. The excitation table is that I know what value is stored on the flip-flop 0, 0, and I also know what value I want after the next clock. To achieve this goal, what should be the input of the flip-flop? So that is the conclusion of the excitation table. If I have 0 and I want 0, what should be the input? If I have 1, I want 1, what should be the input? If I have 0, I want 1. If I have 1, I want 0, what should be the input? Now we can conclude it from here. If there is no change, the value of T is 0. But if there is a change, the value of T is 1. It means in excitation table, if in the present and the next state I don't want any change, doesn't matter what is the state, whether it is 0 or it is 1, the value of the T remains 0. And if I want any change in the state of the flip-flop, if I want 0 to be 1 or if I want 1 to be 0, I want any change, I need to provide the input T as 1. I need to use that flip-flop in the toggle state. Fifth step is we need to make the state table of the counter. As we know, we are designing a 2-bit synchronous up counter. So how many possible state I have? This is 4. Let's suppose QA is LSB flip-flop, QB is MSB flip-flop. QA and QB is the present value of the flip-flop. QA plus is the next value of the QA flip-flop. QB plus is the next value of the QB flip-flop. So if the state is 0, 0, the next state should be 0, 1 in the up counter. If the state is 0, 1, the next should be 2, which is 1, 0. If the state is 1, 0, the next should be 3, which is 1, 1. If the state is 1, 1, the next should be again 0, 0. So this is the state table of the 2-bit up counter, which can be easily designed from the state diagram, which we have already seen in the previous step. The next step is we need to map the excitation table over the state table. We have the excitation table of the T flip-flop, which we have designed in the previous steps, and we have the state table till here. First 4 columns: QB, QA, QB plus, QA plus. This is the state table. And we need to do the mapping of this excitation table over state table for each flip-flop. First, we are going to look at the A flip-flop. So if the value of A flip-flop is QA, what is the next value, which is QA plus 1? If in these two values I want any change according to the state table, the value of input for A flip-flop, which is TA, that become high. I will use it as toggle. QA is 1, I want 0. Again I need to give the toggle state. This is the mapping. It is 0, I want 1. Again it's the toggle. This is 1, I want 0. Again I need to give the toggle state. For B flip-flop, the value QB is 0 and I want 0. No change is there. So the value of TB is 0. In next column, the QB is 0 and QB plus is required, which is required is 1. So I will give the toggle input 1. QB is 1 and QB plus is 1. So no change, I will give the input 0. QB is 1 and QB plus is 0. So change is required. I will give the input 1. So this is the mapping of the excitation table of your state table. Now next and the final step is that from the state table we need to find the relationship between TB and QA/QB and also TA in term of QA/QB. It means we need to solve the K-map for TA and TB, where my input variable are QB and QA. We are going to neglect this value QB plus and QA plus. Now if I'm going to fill this K-map, on row I have QB value, the value of QB is 0, the value of QB is 1, the value of QA is 0, the value of QA is 1. So I'm going to find this equation for TA in term of QA and QB. I need to fill this column in the K-map. I need to fill this column in the K-map. All the values are 1, 1, 1. So I'm going to fill 1, 1, 1, 1. After filling the K-map, we need to do the grouping, and it is easily visible the one quad is possible in this case. And if this quad is possible, I can say the value of TA is always equal to 1. For second variable TB, I'm going to fill this second column, which is 0, 1, 0, 1, 0, 1, 0, 1. And if we're going to make the grouping here, one pair is possible. So if I'm going to find the value of TB from this side nothing is common. Sometimes the value of b is 0 and the sometime value of b is 1 in this particular group. But the value of QA is always 1, which is common in this particular group. So I can say that my TB is equal to QA. So my final Boolean equations for this TA and TB are TA is equal to 1 and TB is equal to QA. By using these Boolean equations, we are going to make the circuit diagram for the required counter. We have these two Boolean equations, TA is equal to 1 and TB is equal to QA. We are going to consider two flip-flop, flip-flop A and flip-flop B. Both the flip-flop are T flip-flop and the negative S trigger flip-flop. I'm going to design a synchronous counter. It means the clock of each flip-flop is common. Now if TA is 1, it means the input of A flip-flop, which is this T, always need to be connected with the VCC. And if TB is equal to QA, it means the output of the A flip-flop, which is QA, need to be connected with the input of the B flip-flop, which is T. Now we can take the final output of this counter circuit from QA and QB. This circuit will satisfy the 2-bit up counter condition, which can be analyzed by using the state diagram. Can analyze if the first clock comes, the initial value of the flip-flop is 0 and the initial value of this flip-flop is 0. Flip-flop A is always connected with the VCC. It means it will toggle at every clock. But flip-flop B depend upon the output of the flip-flop A. If the output of the flip-flop A is 0, for that particular clock, flip-flop B will not toggle. It means after the first clock, flip-flop A will toggle and become 1. But due to this 0, flip-flop B will not toggle and it will remain 0. In the next clock, flip-flop A will toggle always. It becomes 0 and it becomes 1 in the next clock. But in the second clock, the flip-flop B will toggle because the value is 1. So this will become 1. In next clock, flip-flop B will not toggle because the value is 0. So it will remain 1. So you can see the count is 0, 0, 0, 1, 1, 0 and 1. This is the simple working and designing of 2-bit synchronous up counter. In next video, we are going to understand the working of synchronous 3-bit up counter. If you have any doubt, please ask me in the comment section below. Thank you.